those data races.
I talk about SDNRacer, and it basically is a tool we developed concurrency analysis for software-defined networking. This work has been in collaboration with Jeremy Mazier's Bavol in Veshev. And this tool, by the way, is available, and you can download it and play with it online there. So, in a nutshell, if you want a slide to look at what SDNRacer is trying to do is basically on software-defined networking controller at race freedom violations, and these violations are actually, as we kind of show later, actually like sort of bugs as well. We're talking about the SDN. So the main idea that's some kind of code that this flow table. This flow table go and try to find. In this example, we matched action that will be taken out with. It matches more than one. Let's go to a more real example. So, and this is basically this application is replicas. I have in the middle here is just a small network that's controlled by my SD. So this is the pseudocode of the next replica. Then and from the replica back to the source to send back the switch, write a flow entry to forward the packets of the plane, so it continue its own way. I will visualize the recorded of S1 and S2. So at the beginning, this request will hit S1. S1 will say, okay, the entry that matches it, so send it to the controller. The controller say, S1, so it will install a path from S1, S2 to predicate, which basically match packets that the controller sends the flow mod message, like a message, a write message. And then do the same thing to the host, so send it out to the internet here, and it would issue then the packet out, send back the packet. And then we will trigger a read event. This packet entry that would match this packet. I have here an entry. SDN implementation allows the switch to reorder the before the write was committed to the flow table. Match this packet. So the S2 will compute a path all the way to replicate 2, and this along that path. So we will write on. But what we really have here now is a forwarding loop. Again, back from S2 to S1. And this is a real bug in floodlight controller. And as this bug actually is interference in the flow tables, where they're traversing this network. And then how to have a precise notion of the interference. We report only the violations that actually are harmful for the network. Like the reports of these races, properties, and violation and packet coherence. We show what really we data race when we have an order event. Asynchrony here is the right number here, like system. So we need a use SDN, and in a very for the first or the controller when it receives a back. So this is what the happens before model would look like. A packet out, and the packet out caused another read here. Directly on a trace that we actually got from. Very imprecise, just applying directly the habits. So we asked ourselves how we can reduce And what we actually see, it's actually these two events would not actually harm the network in any way. Fields. Also, we have a network. So how look at the flow table now as an abstract data type. A specific flow entry on that on the existing one as well. Same net effect on the sometimes the open flow specific implementation, and we try to see what people actually are using. Very general way of defining community specific. Here we have an example whether to add operation priority to check if they're commuting or not. All the events that are not ordered, such that one the same flow table. But when we apply the commutativity rule, we go down to only one race. That's a huge reduction for just a toy example. So let's see how that does in actual trace. So we go down, when we apply this on the floodlight trace, we go down from 700,000 to 18,000, which is a huge reduction for just using one simple idea. But we still have 18,000. Okay, we can do better than that. So there's the other category of races, the category of races that are infeasible. So let's say, for example, I have a write event, and then I write a switch. And then 5 minutes later, I go and read that flow table. Well, actually, networks will not reorder these events because they are far apart on time, so they will not be reordered. So how we can capture this? So we add a time-based filter, and basically this time we'll add happens before edges between events that are far away in time, and they cannot be reordered due to physical limits. And some other studies actually studied these things, and they quantified the time window where an open flow switch would actually reorder events. And this time value is that such that it's safe that the switch will not reorder events. It can be provided as a parameter for our tool. So when we apply this, we get overall reduction from 700,000 to 2,000 events, which is a huge reduction in terms of the reported races. I just like to point out, actually, this is probably the nastiest bug we found in our tool. And because you have seen, because this bug would actually cause the switches to go all the time and send packets into the controller. So we have actually order of magnitude more read and write events on the trace than other traces we have tested with. And basically, the controllers and switches will be sending back and forth read and write events. But in all other traces we have seen, the median was about 24 races reported. This is probably the largest number of races. Then the question is, basically, comes out, okay, can we leverage this to the race detector component to check for higher level properties? That properties that the network operators will care about, like, and we can show, like, okay, these are races, but you can also check for higher level properties, and potentially maybe you just only look at the races that actually affect these properties. So this is the next type. This is the next section of my talk, and In particular, we check actually for two high-level properties: network isolation, network update isolation, and packet coherence. But first, let me try to define what is a network update. So we define network update as a set of write events that reflect high policy change. So if we go to our example, so we have here the event trace. And in reality, we have two versions in the network. The version 1, the update number 1, basically says forward the packets to replica 1. And the second version says forward the packets to replica 2. So what's about our property? So the property that we test for here, the isolation property. And basically we're saying two network updates are isolated if they can be serializable. And how we check this? The check is very simple for this. We just check that there is no data race between two write events such that they are in two different update sets. So if we go back to our example, in this case, we have two write events and they're actually racing with each other on the same switch. And then we can say they are not serializable, so we have violation of this property. And the second property we check for is packet coherence property. And packet coherence property says basically your packet will be processed entirely using one consistent global network configuration. So if we go back to the same example, our packet actually was read by two versions, and we have a violation. And that's why we have the loop, because one version was saying, go from S1 to S2, and another version saying go from S2 to S1. If you take these two different versions and use the existing tool like header space analysis to check if these versions are correct, they will tell you they're correct, but the interleaving between them is not correct. So how we check for this property? Basically, the check is very simple. When the packets first hit the first switch, we take a note of the version that actually it processed that packet, and then for the rest of the lifetime of the packet in the network, we check if it does race with any other write events from different versions. So some guarantees here, because we leveraging the happens before model. SDNRacer checks will actually guarantee that the property will hold for any reordering for the given trace, which means that you actually check for less traces. Basically, we check only for different traces, but you don't have to check again and again if you have reordering in the trace. Now we come back to the implementation evaluation. So we implemented some instrumentation to instrument how the read and write events happening in the network. So we instrumented an existing tool that was published 2 years ago called STS. And basically, this STS will simulate an SDN network and test it against existing controller. And basically, we record all the read and write events, and we output it to a single file. Then offline, our tool take the concurrency analysis, take this file, and apply the concurrency analyzer we talked about, like the happens before model, the cumulative specification, and the time-based filter. And then we check for the high-level properties. This code was about like 3,000 lines of code, of Python code, in addition of what STS already have, and it's available online again. And then for the evaluation, we tested with 3 controllers, off-the-shelf controllers. We have Onos, Box, and Floodlight. We can test with these controllers as black box, or to reduce the number of false positives, you can actually also add additional instrumentation. So for these, we added some like less than 100 line of code instrumentation just to instrument the open flow I/O loop to increase the precision of our tool. Very to have. So for the applications, we tested with applications. These are the 5 applications we tested with. Applications in the paper, but I just want to point out not controllers. So whenever the application is available, we test with it. When it's not available, then it's not. So we test with 3 network topologies: single switch, 2 switches, binary trees. So, and we run every controller and every application if possible, and we generate random packets randomly in the network. So we collected a total of 29 traces. So SDNRacer was able to the races compared to just directly applying happened before its model. And in the best case, we reported only one race. The median was 24 races. So overall, you have a reasonable number of races that someone can look at what can be done. And for detecting bias, when we applied high-level properties, we detected two update isolation violations. The one we already talked about, the floodlight load balancer. And this bug is easy to fix before sending the packet back to the network. And the second bug was with forwarding module in box. Actually, we talk more elaborately about these bugs and the details of these bugs and how to fix them and suggesting how to fix them in our paper. Now, time-wise, we actually, in less than 30 seconds, our worst-case scenario traces generated, and the worst case was 3.7 minutes. This is, by the way, aggregated over all the traces we tested with. But still, like 3.7 minutes is not too bad for such a nasty bug. Conclusion, what we have here is a habits before model for SDN that we can capture asynchrony of SDN networks, and a flow table commutative specification to capture interference in more. To point out, these two components are general and can be also used in other contexts. Analysis for SDN. But in this exam, it's focused on the concurrency analysis, and we try to and packet coherence. Also, we have this implemented online, and it's actually reported some bugs, some interesting otherwise to find with existing tools and real controllers. And that's it. Thank you.
So, sorry, maybe I missed this, but how did you come up with the commutativity spec? And is it possible that
so the commutative spec we came with by just studying the OpenFlow specification manually. False negatives, we don't have false negatives, but you might have false positives. And this is basically just a guarantees that we get for false negatives from the happens before model.
Thanks.
Hi there, Joe DiVietti, University of Pennsylvania. I think this is really interesting work. Good job. One thing I was just wondering if you could say a little bit more about it is how do we fix these races? What does synchronization look like?
So the synchronization look like, so OpenFlow, for example, have the using barriers such that after a write event, after you issue a set of write events, you add this message called the OpenFlow barrier. Until after the switch commit all the writes, it will send you a message back. It's like, hey, I committed the writes. And then the controller can. Does that answer your question?
Foster Cornell,
Hi.
Really cool work. I'm curious if you think it would extend to some of the newer data planes that are being proposed. For OpenState, there you might have multiple parallel pipelines, you have mutable state, and so all these bugs that you've seen in kind of the simple OpenFlow case would blow up even further. If you could specify them using this framework, that would, I think, be quite powerful.
Exactly. So yes, that's it. Can be done. So this spec actually implemented for OpenFlow specifically, and to be specific, OpenFlow 1.0. As I understand, in B4 you still have the, so you just can take the same work and apply it directly. But if you have a more different interoperation for the switch, then you have to come out with a different spec. Other work it's kind of interesting for me to actually try to learn this commutative specification directly. That would be really interesting because just coming and sitting down and writing these and an effort.
Hi. So, what's the story of bugs and races are going to happen once you've gotten into some? So how do you know you've collected enough traces, enough of your sort of complex SDN application?
So right now, we have is for specific inputs and of inputs. So what we try to do is like, okay, are given to your network, then we just try to guarantee your controller will do fine. Doing a more stateless model checking, and that would be really interesting too.
I'll ask the last question. One thing I didn't understand when you were talking about the higher level checks that you notions like update sets and versions, which you were talking about, seem notions. So how do you know what those are just from a trace of events?
So for reactive applications, and the controller respond with a set of write events that but when the controller arbitrarily decides it's going to do an update, the controller to mark these updates for you, and but for the purpose of this paper, because we didn't want to modify the controllers, we're going to treat them as black boxes. So what we used basically we time these write events, and then we cluster them based on time. And then if they are, we assume they are a part of some update together. And also to might have some problems, then we merge some of these sets if there is a transaction going here, and then they wait for the barrier. That's because that's them again. So we have some heuristic to do this, but the work.